Welcome again to my classes on fundamentals of electrical circuits. We were in the fifth section where we were discussing AC circuits. We already covered a few easy problems. I suppose they're easy. And we went on to do problems which are associated mostly with the frequency, both in terms of resonance as also without resonance, and how omega is helpful in solving the circuits. And it's also required as to how look at the omega component of the sinusoidal wave is going to be important. Okay, so we also talked about both kinds of representations. The phasor representation, wherein we have the RMS value with an angle, or as a sinusoidal waveform where we have a maximum value, the sine value, the sine or the cosine waveform, and then there is an omega t component, and then either there's a lead or a lag. Okay, so lead or lag, when you're talking about a phasor, as is mostly covered in this section, we'll talk about with an angle 0 if there is no lead or lag, with a negative angle phi where it is lagging, and a positive angle phi where it is leading. Okay, so it depends upon the quantity. Okay, so let's look at the first problem, and let me hope that the phasor aspect can be made clear as we move through these problems. Okay, the voltage applied to a circuit, so it's all English, so we have to read. The voltage applied to a circuit is 100 root 2. So maximum value is 100 root 2, which means that the RMS value is 100. Okay, cos 100 pi t, which means that omega is equal to 100 pi. Okay, and the circuit draws a current of, okay, so this is the voltage applied, and the current drawn is 100 root 2 sine. Okay, so now the phase angle has shifted, 100 root 2 sine 100 pi t plus pi by 4. So what all do we have? We see that there's a maximum value 10 root 2, which means that the RMS value is 10. Okay, since the angle, since from a cosine waveform we have shifted on to sine waveform, we'll have to convert it into the same kind of waveform shapes. Only in that case we'll be able to look at the angle of lead or lag. Okay, and 100 pi t is the same, so which means the omega is the same. But then in this case it appears as though there is an angle of lead, but we are not very sure because both are not in the same format, okay, or of either a cosine form or a sine form. Okay, taking the voltage as the reference phase. Okay, so now phasor. So the voltage is taken as a reference phasor. In that case, it should be shown as equal to 100 angle 0. Okay, the phasor representation of the current is. Okay, so as it is, I would also recommend to convert the sine into cosine, because it's always easy to give a pi by 2 and also remove a pi by 2, or in other words, sine 100 pi t plus pi by 4 plus pi by 2 minus pi by 2 can be taken into consideration, where pi by 2 plus the rest can be taken will yield a cosine. That is, the sine will be converted into cosine. Okay, so now we have only what is minus pi by 2 is left. So minus pi by 2 and plus pi by 4 will give us minus pi by 4, which tells us that there is an angle of lag. Okay, because now they are both of the same format, that is having a cosine waveform. Okay, so taking the voltage as reference phasor, the phasor representation of the current in amperes is. Okay, so there is absolutely no problem, since phasor representation is asked, then 10 by root 2 becomes 10, because it has the RMS value, and the angle has now, since sine has been converted into cosine, okay, we see that we are having pi by 4 minus pi by 2 or minus pi by 4. So answer B is correct. Okay, so I suggest that in such cases always go for conversion from sine to cosine, otherwise you will be stuck with a negative value, which might create problems. Okay, but we have to do it in certain cases. Let's hope that we'll be able to follow that out. Okay, so phasor is an RMS value. Okay, these are 2 points that that I'd like to make clear at this juncture. Then moving on to second problem. A two-phase load draws the following phase currents. I1t is equal to Im sin omega t minus 5, and I2t is equal to Im cos omega t minus 5 by 2. Okay, so any of these can be taken into consideration. Okay, so better to convert the cosine also. There's no problem at all, because what is asked is these currents are balanced if phi 1 is equal to. Okay, so if you convert cosine to sine, what happens is that you get a negative sign. Okay, so that can give rise to what is called as easy that balancing act. Okay, so now we see that you can, when you give a pi by 2 and a minus pi by 2, so pi by 2 plus cosine of pi by 2 plus certain things will become a sine. Okay, so now we have what is called as minus phi 2 and minus pi by 2, because pi by 2 has already been taken into consideration. So what is angle phi 1? Phi 1 now is the same as equal to, so if you balance them, phi 1 is the same as equal to pi by 2 plus 5. Okay, I suppose this logic is also taken is also made clear to you, especially because in the earlier case we dealt with the conversion from cosine to sine. In this case, just for balancing, that is both are one is opposite to in the direction to the other, we have converted cosine to sine. Okay, so as in what the opportunity offers, you will have to make the conversion. Okay, so here we did that. So plus pi by 2 into plus pi by 2 plus omega t minus phi 2 minus pi by 2 was converted into sine. Okay, with a minus sign. Okay, so now we can balance. So we see that minus phi 2 minus pi by 2 is equal to minus phi 1, and so so automatically phi 1 is equal to pi by 2 plus phi 2. Okay, so I suppose we are clear about the conversion and what a phasor is. Okay, with the RMS value with an angle. Okay, the voltage across, so problem 3, the voltage across the currents, voltage across and the current through a load are expressed as follows: Vt is equal to minus 170. Okay, sine 377t minus pi by 6 volts, and It is equal to 8. Okay, so it's not sine, it's cosine there, but see 377t is okay, which means that they have the same frequency. Okay, plus pi by 6. So many amps. Okay, the average power in watts rounded off to 1 decimal place consumed by the load. So that's what we are going to do. So first we plot. Yes, first of course, as before, let's convert from sine to cosine, because it's so the negative sign is retained, and negative sign is good because only in that case it becomes a load, that is the current and the voltage are in opposite direction. Okay, so now let's draw Vt. So it is sine 377t minus pi by 6. So let's add pi by 2 as also remove pi by 2. So it becomes cosine. So okay, so we have pi by 2 and minus pi by 2, which means that pi by 2 is already taken into consideration. Minus pi by 2 means that you are having pi by 6 is 30 minus 90 minus 120. Okay, as shown by the red line here, we have the voltage now lagging by 120 degrees. Okay, and then the negative value can be brought can be reflected and taken to the other side. Why we'll see soon enough. Okay, so now let's look at let's plot It. It has a value equal to 8, unlike while the voltage is 170, and we see that 377t. So omega is okay. So we can use these two quantities to calculate the power without any problem. And this plus pi by 6. So plus pi by 6 means 30 degrees. So I have drawn It using a red line here with a magnitude equal to 8 and an angle equal to plus 30. So I suppose all these aspects are clear. First we go for converting the voltage from a sine to cosine. So we have minus 170, and then since both have the same omega value, you can compute power in the conventional sense itself. So 377t ensures that, and then we are seeing that it's equal to minus pi by 6. Okay, so from sine to cosine, such that you can afford to calculate the power. You have what is called as giving and taking a pi by 2 to it. Okay, so when you give a pi by 2 to it, it becomes cosine and with a positive sign. Okay, there's no change in sign. Okay, and then minus pi by 2 will give you minus pi by 2, which is minus 90, and minus pi by 6, which is minus 30, in total giving you a angle of minus 120. And that's the reason why the direction moves in a clockwise sense. Okay, and so we see that minus 120 is the red line which indicates Vt. But then it is reflected back because we know that it is a minus 170. Okay, so now they are both in the same quadrant, and this is important for calculating power. Okay, why? Because now we have to take the phasor value of the voltage, which is 170 by root 2, the phasor value of the RMS value of the current, which is 8 by root 2, multiply them together and find out the angle between them. The angle between them has to be less than or the most equal to 90 degrees. That's the reason why we are reflecting back VT. On the other hand, it is also telling us when it's not reflected back, it's also telling us that it is a load. Okay, it's only when it's a source that we have them in the same quadrant. Now we have them in different quadrants, but just to compute the angle, I have reflected it back, and so now we are having minus VT there, and the angle between them is now. So when an angle of 120 degrees is reflected back, it will create a 60 degrees with respect to horizontal. Okay, 120 degrees with respect to horizontal, when reflected back, will create a 60 degrees with respect to the horizontal. So 60 degrees and 30 degrees, the difference is 30. So it's very easily 170 by root 2 into 8 by root 2 into cos 30 or which is root 3 by 2, and that answer is going to be 588.9. Okay. Moving on to problem number 4. The circuit shown the figure with R. Okay, so the figure is shown. We have three elements, all the three elements, and voltage VT given across it, with the current flowing into it as into this sub network, which is IT. Okay, the current shown in figure R equal to 1 by 3 ohms, L equal to 1 by 4. Henry, and capacitor is equal to 3 farad, has input voltage VT is equal to sine. Okay, so magnitude is 1, 2t or omega equal to 2. There's no lead or lag angle. Okay, so magnitude is equal to 1, and sine is and omega is equal to 2, and the resulting current has to be calculated. Okay, current IT is the instantaneous value of the sinusoidal version is to be calculated, and the answers are all in sine. So we can easily calculate by finding out what happens to the current components that are drawn by the resistor and the inductor and the capacitor together. Okay, because inductors and capacitors have opposite reactions. So if inductor is drawing a positive current, then it will be negated by the capacitor drawing a current. Okay, they act 180 degrees with respect to each other. Okay, so now we have, so what is so we have voltage as equal to 1, and 1 multiplied by the admittance of resistance 1 by 3, which is 3. Okay, so we have one component which is equal to 3. Okay, so and then we have the other two components, that is y is equal to we have so we have omega is equal to 2. So omega L is 2 by 4, 2 into 1 by 4, 2 or half, or its admittance value is equal to 2. Okay, and the capacitance is equal, but of course the impedance value is half. Okay, the capacitance is given by 3, and its impedance value is given by 1 by 3, and 1 by 3 omega, or 3 into 2, or 1 by 6. Okay, so its admittance value is 6. Okay, admittance value is larger, but its impedance value is smaller, which when compared to the inductive reactance, or in other words, it will the current drawn will be lagging in nature, generally lagging in nature. Okay, so this is also understood. Okay, so now we are having 1 into the overall reactance, which is 4. Okay, so we are having 1 into 4 and 1 into 3. So together 3 and 4, they are at 90 degrees with respect to each other. So 3 and 4 combined together to form 3 square plus 4 square, square root of that, which is equal to 5. So answer 5 is right, but of course A and B are talking about answer 5. Okay, the magnitude, the total magnitude. And regarding the angle, we see that there is an angle of lag. Since both the angles are the same, we can choose this as equal to minus 53.1, because the inductive reactance is larger. Okay, at the same time, please remember, I hope you remember the earlier instances when we had 3 plus J4, wherein a larger angle of 53.1 was indicated there. Okay, when it is 4 plus 3j, okay, then the magnitude is 5 as in the early case, but the angle is going to be 90 minus this, or 36.9. Okay, so just a recalling of what we have been discussing earlier. Okay, so moving on to problem number 5. In all these cases, perhaps you notice that more than the diagram, it is what is written in language which is going to be important. So reading is very important. Okay, in this case, reading correctly and understanding then and there. Okay, that's the reason why I interrupt and interpret as we go along. Okay, while we read the problem itself. An input voltage VT equal to 10 root 2 cos t plus 10. Okay, So that's not enough. There are more parts to it, but at the same time the phasor value is 10 and omega is 1 in this case, but there is an angle of lead as given by 10 degrees. So in phasor it would have been represented as 10 angle 10 degrees. Okay. Now we move on to the next component. There's another voltage component as well. It's a harmonic because we already see the cos 2t there. Okay, it's the second harmonic. Okay, and the magnitude is equal to 10 root 5. So cos 2t plus 10 degrees. So both of them have the same angle of lead, which is equal to 10 degrees. Okay, but there are two voltages at two different frequencies. Okay, so you can of course apply superposition. There's no harm in applying superposition. Okay, it's applied to series combinations of resistor 1 ohm and inductance 1 Henry. Okay, so this 1 Henry is now problematic because when it faces the voltage component 10 root 2 cos t plus 10, it has an impedance or reactance as given by omega L or 1 into 1 or 1. Okay, but on the other hand, when the other bit of voltage arrives on the scene, it now gives rise to another kind of reactance, another value of impedance as given by omega L again. So L is remaining constant, but omega now becomes equal to 2. Okay, so this is the most important thing that we need to remember. That is, in the first case we are having a different impedance, and in the second case we are having a different impedance altogether. The first case is going to be 1 square plus 1 square root of that or root 2. Okay, so Z is equal to root 2 when we consider the application of voltage component with omega equal to 1 alone, and then to it we will be adding the next component. So the next component, when applied alone, will see an impedance as given by root 5. Why? Because R is equal to 1, but omega L has now become equal to 2. Okay, so 2 square plus 1, that's equal to 5, so square root of that. So there are two impedances facing the same voltage, but of course the voltage components are different. Okay, so that's idea number 1. And now let's see what is asked. Okay, the resulting steady state current IT. Okay, so now there are two bits of currents, one at frequency 1 and another at frequency 2. Okay, so what do we have? We have two different impedances also. Let's see component number 1 is applied, and then we see that we are having impedance is equal to root 2 and an angle of lag by 45 degrees. Why? Because both resistor and inductor happen to be the same. Okay, resistor ohmic value and the inductance ohmic value or reactance happen to be equal to 1. So 1 square plus 1 square, and the angle between them is equal to 45 degrees. Okay, so the first component will be the same is equal to 10 by root 2, that is the voltage, divided by the impedance, which is root 2. So 10 again. So since we are giving the sinusoid waveform and not the phasor, so we have 10 and cos t plus 10 minus 45 because it's inductance. So we have an angle of lag due to inductance. So it's minus 45. So it's going to be equal to minus 35. So of the four answers, we see that C agrees to some extent because it is 10 cos t minus 35. Okay. And now moving on to the next bit, when we are having 10 root 5 cos 2t plus 10 degrees applied, we see that it has an impedance as given by root 5. So divide by root 5. So the answer is again going to be 10 root 5 by root 5 or 10. Okay. And now we are having an angle as given by the change in pattern of the inductive reactance, which is equal to now 4 and so 2 into it's equal to 2, and we have now resistor value remaining the same as equal to 1, so 2 by 1. Okay, so that is tan inverse 2 by 1 is going to be the angle of lead. Okay, angle of again in lag because it's still it's still an inductive reactance. So we see that 10 root 5 by root 5 or 10 into cos 2t, the frequency does not change, plus 10 degrees, that also remains, minus tan inverse 2 by 1 or tan inverse 2. Okay, as simple as that. I suppose the three concepts that are included in this problem is clear to you. First and foremost, we see the voltage as a combination of different voltages, and each of these voltages are applied one after another, and then the outcome is summed together, or you use superposition. Okay, for using superposition, we have to realize that the impedances vary, and therefore the angle of lag, because it's always inductance, the angle of lag also continues to change. Okay, so what is the impedance in the first case? It's equal to 1 square plus 1 square, square root of that, or root 2. Okay, in the next case we are having the omega changing to 2, so omega L is equal to 2, or in other words we have the impedance as equal to square root of 1 plus 4, 5. Okay, so root 5. Okay, and in both cases, the angle of lag also changes. In the early cases, it is tan inverse 1 by 1, which is 45 degrees, or pi by 4. Okay, in the next case, it's going to be tan inverse 2 by 1, or in other words, it's going to be yes, simply tan inverse 2. Okay, so if the angle is given, you can calculate that. Okay, so now we are ready to fit together the two currents that come about as a result of giving two different voltages. So first quantity is 10 cos, no change, t minus 35 degrees plus 10 cos 2t plus 10 degrees minus tan inverse 2. Okay. Moving on to the sixth problem. For the circuit shown in the figure, the voltage VC in volts across the capacitor. Okay. So what do we have here? We have 5 sin 5t. So amplitude is 5, magnitude is 5, and the omega value is 5. Okay. And then we have two resistors. Okay, they are all in series, so it's equivalent to 200 kilo ohms. Okay, and we also have 1 microfarad. Immediately we can convert 1 microfarad into its own ohmic value as 1 by omega c. What is omega? Omega is 5. So 10 raised to 6 divided by 5, that's equal to again 200 kilo ohms. Okay, so 200 kilo ohms of capacitive reactance and 200 kilo ohms of resistor. Okay, so the angle is going to be pi by 4 because they happen to be of the same value. But in this case, the current is going to lead. Okay, and what is asked out of us is that the voltage across the capacitor. So the voltage across the capacitor, you simply divide the voltage divide the voltage as a potential divider. But of course, it's a vectorial kind of division. Please remember that. Or in other words, 5 has now to be divided between a total impedance as given by 2. Okay, so since it's all in voltage, we can just since both the numerator and the denominator will be in a potential divider will be in kilo ohms, we'll just take the numerical value. So we have 2 square plus 2 square, or 2 root 2 on the denominator, and 2 on the numerator, because we are trying to find out the voltage across the capacitor. Okay, so we have 2 by root 2. So 5 into 2 by root 2 is the same as equal to 5 is the same as equal to 2.5 into root 2. Okay, and then we also have what is called as an angle of lead. Okay, so of course now the current is going to have an angle of lead, but the voltage is going to be lagging. Okay, that's the reason why we are having the current that flows in this series circuit is going to be leading the voltage, but the voltage has to lag, and that's the reason why we say that it's the same as equal to 2.5 into root 2 sine 5t minus 0.25 pi, or pi by 4. Okay, I hope it's clear, and the diagram also makes the potential divider very clear to you. Okay. So now moving to problem number 7, we realize that the circuit has a 4 angle 0 voltage, that is RMS value, with no angle of lead or lag, feeding two impedances directly and the load RL. Okay, so across RL there is a J2 ohm resistor, J2 ohm reactance, and there's a 2 ohm resistor as well. Okay, so it's a potential divider there as far as we can see. And let's see what the problem is. In circuit, the maximum power in track watts. Maximum power means Thevenin's theorem. Okay, that can be transferred to the load RL, and the maximum power is given by VTH square divided by 4 RTH. So we have to ZTH. Okay, in this case ZTH. Okay, so we have to find out ZTH by looking from RL. Okay, since there aren't any dependent sources, we can directly short circuit the voltage source 4 angle 0 and obtain two parallel J2 there. When looked at from the point of view of RL, so that's equal to 1 plus J. I hope you remember that when we have A and JA in parallel, the series combination is equal to A by 2 plus JA by 2. On the other hand, if it is A and minus JA in parallel, then it's going to be A by 2 minus JA by 2. Okay, so the series combination we have already obtained as the Thevenin's impedance as 1 plus J. Okay, you can also do the conventional aspect, and you can see that the magnitude is going to be root 2 now of 1 plus J. Okay, and then this voltage 4 angle 0, since RL is open circuit, it's getting divided between the two impedances. of course vectorially. So we have on the denominator the vectorial addition of 2 and j2, which is equal to 2 root 2. So we th, that is 4 divided by 2 root 2 multiplied by 2, because 2 is going to be the impedance value of the reactance J2, which is across R. Okay, so VTH is equal to 2 root 2. Okay, so now it's simply VTH square, that is 4 into 2, 8 divided by 4 times root 2. Okay, so that gives us 1.656 watts as the maximum power which is transferred. Okay, moving on to the 8th problem. A lot of reading, but as we read, let's also may process the whole material. Okay, a series RLC circuit is observed at two frequencies at omega 1 equal to 1 kiloradians, that is 1000 radians per second. We note that source voltage V1 is equal to 100 angle 0, results in a current equal to I1 is equal to 0.03 31 degrees. So the 0.03 looks a little too problematic, because that means a lot of impedance, but let's not bother about that. But the angle is near around 30 degrees. Okay, so and it's an angle of lead. Okay, so the reactance, the capacitive reactance must be predominant here. Okay, at omega 2 equal to 2 kiloradians per second or 2000 radians per second, the source voltage V2 is equal to 100 angle 0, results in a current I2 equal to 2 angle 0. So both are in phase. Or in other words, we have a case of resonance happening at 1000 hertz. Okay, at 2000 hertz. Sorry, at 2000 hertz. The closest value of RLC out of the following options. So many options are given. The first processing that we will be doing will be to process the phenomenon of resonance. So that means that the resistance value is going to be, and that is the circuit is going to be purely resistive, and it will be given by 100 by 2. Okay, or 50. So all the answers reflect 50. So that we can leave aside. Now we go to the next point. The next point regarding reactance is that at that point XL is equal to XC. Okay, so all the values, if you multiply by, if omega L values, all you can multiply by 1000 by 2000, because that's the frequency at resonance. And the capacitance values you can find out 1 by omega C, and you will see that everything matches. Okay, just do it roughly and you will see that everything matches. So that's not going to be a solution, but that's another pointer. Okay, now we move on to the third aspect. What is that? We look at the first statement wherein it is said that at omega 1 is equal to 1000 radians per second, V1 and I1 are connected via an angle of lead which almost equal to 30 degrees. Okay, so if the angle is almost equal to 30 degrees, then we know that at approximately 30 degrees, Z into root 3 by 2, whatever be the impedance, which has both resistance as also the reactance, gives rise to the uniform resistance that we have, which is 50. So Z into cos 30, which is root 3 by 2, or Z into root 3 by 2 is equal to 50. So the reactance value will be obtained by the sine multiple. Okay, or in other words, Z or sine multiple of Z. So Z is equal to 50 by 50 into 2 by root 3 multiplied by half. So 50 by root 3, which is near around 28 or 29, near around 30. Okay, so almost 30 is the value of which we obtain as the reactance value, which is equal to 50 by root 3. Now we can just simply compare. Let's take case A, where we see that for 1000 radians per second, XL is equal to 25. Okay, 25 millihenry becomes 25. Okay, and XC becomes the same as equal to 10 raised to 6, that is for micro, divided by 10 and another 1000. So it's going to be 100. Okay, so 100 minus 25 is 75, too big. Okay, of course capacitance reactance is predominant, but then 100 minus 25 is going to be 75. We want a value near around 30, a little below 30. Okay, rather a little more below 30. Okay, so now we move on to answer B, wherein we can try to find out what is the XL value. XL value is the same as equal to 10 into 1000, 10 millihenry into 10,000, or 10. Okay, so 10 ohms is XL, and XC is given by, again, 10 raised to 6 divided by 25 and another 1000 because of omega. Okay, so we see that that's equal to 1000 by 25. That's equal to 40. So 40 minus 10 is near around 30. So answer B is very near to the answer, and that's exactly what is asked. You can go beyond also. You'll see that answer B is correct. Okay, so you can see that. Okay, so this is a method of solving the problem. That's all that I'm trying to say. I'm not saying that this is the only way. Okay, so moving on to further problems, where we have the ninth problem. We have more problems in AC circuits, because there are and these four sessions, if you study very well, repeat at least twice, then you'll be able to do any AC problem. Is what I would say. I would like to say to you. Okay, moving on to the ninth problem. For the circuit shown, we have a circuit wherein we have an input resistance R1, and then we have a combination of R2 and C in parallel, across which okay, of course, when you apply a voltage and the current flows through it, you get an impedance as given by ZJ omega. Of course, it depends upon omega. Okay, and we also have the real value of Z and the imaginary value of Z, because they are the functions of omega plotted. Okay, so we see that. Okay, so now we see that the real value is important, because real value gives us the value of either R1 or R2 or a combination. Okay, so let's see what they are. When omega equal to 0, what do you mean by omega equal to 0? That the capacitor becomes 1 by omega C, omega equal to 0. That is, you are having an open circuit. So the total resistance that that we read from the left end, or what is seen as J omega, where omega is now equal to 0. So we see that now we are having R1 plus R2. So R1 plus R2 is equal to 5. So that's the first analysis. Second is when we see that the real value is equal to 2. At that time, omega equal to infinity, which means that now capacitor is a short. Okay, so if capacitor is a short, because 1 by omega equal to infinity, capacitor is short, then the only resistance left in the circuit is going to be R1, and so R1 is equal to 2. Okay, so R1 is equal to 2, and that perhaps okay, and the question happens to be that for the circuit shown, the locus of impedance J omega is plotted as omega increases from 0 to infinity. The values of R1 and R2 are, so R1 is equal to, as we saw, equal to 2. Okay, so we are having two answers with R1 equal to 2, and then let's see what, so, and R1 plus R2 is equal to 5, which means that R2 is equal to 3. Okay, so there's only one answer which is correct, which is answer A. Okay, so this can also be simply solved, and there's no phasor aspect here, but the frequency aspect is here. Okay, so let's move to problem number 10. The circuit shown, the 3 voltmeter readings are V1 is equal to 220. Okay, that's the overall voltage, as we can see from the diagram. V2 is equal to 122, which is across the resistor, and V3 equal to 136, which is across both resistor and the reactance put together across a coil. Okay, the power factor of the load is, so the load is what is called as RL plus XL, so which is coming RL plus JXL, which is coming as the across which the voltage happens to be 136. Okay, so now what is the power factor? Okay, so a small sort of a vector diagram is drawn at the bottom, where we see that the voltage V1, the voltage V2, which is across the resistor, is horizontally displayed, and then we are having a voltage across a resistor reactance combination, which is shown as a red triangle, and then the overall voltage V1 is mentioned, which is along the diagonal. Okay, so we have all the 3 components here. So how do you find out the power factor? Of course, there are formulae, etc. If you don't remember the formulae, the best value is to see whether what is the value, or what is the power factor if it is going to be 0.5. Okay, why is it 0.5? Is 0.5 useful? Because on one side of 0.5, that is beyond 0.5, there is answer C and answer D happen to give a larger values of 0.5, the larger values of power factor, and A happens to be less. If 0.5 is applicable, then we choose that. Otherwise, if 0.5 tells us that a lower value of power factor is indicated, then we go for 0.45. Okay, so that's or higher value means we go for C. We may have to have one more to do one more computation. That's all. Okay, so so this is a method that I'm suggesting for examinations like GATE, JEE, etc. Okay, so let's move on to so the diagram. So I suppose we know that we have Yeah, so if 0.5 is the power factor of the load, okay, then we realize that that 136, that is the voltage across the combination of resistor and reactance, will have a horizontal component which is the same as equal to half of it. That is 136 multiplied by 0.5, which is the power factor, which is equal to 68. So that will give us a total of on the base we will have 190, and the height is equal to again 136 multiplied by root 3 by 2, which is going to give us 120. Okay, so once you multiply, so 190 and 120 tells us that you can have that is now the triangle is and now it tells us that the triangle is not that the hypotenuse is not good enough, that is the hypotenuse is not long enough, so we go for the lower value, and so we don't even compute, we just go for 0.45. Okay, so that's the way that you can try to do the problem when we see that of the answers what is more appropriate. Otherwise we have a formula for that, you can remember that and do it. Okay, another locus is given in the problem number 11, wherein we read that a sinusoidal source of voltage V and frequency F is connected to a series circuit of variable resistor and a fixed reactance X. In this case, the reactance is fixed, but the resistance is varying. Okay, unlike in the early case where frequency was varying. Okay, locus of the tip of the current phasor I, as R is varying from 0 to 2, is what? Okay, so what is the circuit? What are we getting? Okay, so I have just attempted to draw it. Why? Because you can have several aspects, like for instance R can be equal to 0, R can be equal to infinity, and then what happens? Okay, so when voltage V is applied, okay, and frequency is okay, of course the frequency also remains constant, then R alone changes. So if when V is equal to, when R is equal to 0, then the total the current is given by V by X, because R equal to 0. Okay, and then when R is equal to infinity, then the current is equal to 0. Okay, so that's okay. And then we also see that we have, okay, so now we have from the four different answers, we see that there's a diameter of V by X, so that is okay. So of all the answers as can be shown here, when X is equal to since X happens, when R is equal to 0, X happens to be a quantity with J with it, or in other words there's a minus 90 degrees. That's the reason why the current phasor is drawn at minus 90 degrees with respect to the horizontal. Okay, so we see that there's a diameter there, and then and then another aspect also has been taken. When R and X are equal, then we are having then we see that there is a current as given V by root 2 times X, because R and X happen to be the same. Okay, and then the angle is equal to 45 degrees. Okay, so we see that now it executes, because if the angle is equal to 45 degrees, it will execute what is called as a and then so it will execute a circle. So now we have only a semicircle. That's the reason why the first answer is chosen as right. Okay, so since these are gate examination questions, just the clicking with the answer is enough for you to discard the other answers, and especially you will notice that in gate examinations, answer A or answer B are more often right when we are having a little complex questions, as we have been seeing all through. Okay? Just let us complete the 12th and 13th problem in the last slide in this session as quickly as is possible. So looking at problem number 12, we see that there are two sources, 12 angle 90 and 120 angle minus 90, 120 angle minus 30, oppositely directed, pushing currents through a network of impedances, each of 80 minus J35 ohm impedance. Okay, so now and looking at the answers, they seem to be all equal except for one, and what is asked is the current I in the given network. And where is the current I? The current I is somewhere in between, connecting between the delta of impedances and the two sources, center point of the two sources, okay, feeding the entire impedance. Okay, And when you'll see that and what is asked is the current that flows through it. Of course, the current cannot be zero. So all the other answers, one of the three answers are right, and the magnitude is the same, which is 2.38. So we won't bother about the magnitude. We'll look only at the angle. Okay, that's the reason why the angle of the impedance has been found that seem to be near around 24 degrees or so. Okay, so that's all that's important. Now we'll try to find out the pattern of flow of current. The current that emerges, okay, of course we will apply superposition because there are two sources, that's easier. Okay, so the current that emerges from 120 angle minus 90 degrees volt source follows an outer path and returns, because every current has the tendency to return as through the easiest path available, and so it does not flow through I at all. It does not flow through the path indicated by I at all. On the other hand, there's another branch of current again emerging from 120 angle minus 90 degrees, which flows through that impedance Z and then returns back to the source. Okay, so both these currents are shown in red. The green current paths are a consequence of the voltage 120 angle minus 30 degrees with the positive terminal downward, but at the same time the upper source, that is 120 angle minus 90 degrees, shorted by applying superposition. Okay, so again there is a outer path as also a low inner path for the current. The outer path does not flow through the path shown where I is there. So the inner path alone is important, and that inner path is now allowing a current I2 to flow through oppositely directed to I, as also I1, which is again marked in red, which is again oppositely directed with respect to I. Okay, so these are the so now we need to find out I as a combination of I1 plus I2. Okay, but with the negative sign or oppositely direct. Okay, so that's the reason why we find out the current through the current I1 as equal to 120 angle minus 90 degrees divided by the impedance with an angle minus 23 degrees. Okay, so that gives rise to an angle of approximately 90 minus 24 or so. So near around 60. Okay, so that's why I1 is shown in the diagram accompanying down below, which shows that near around minus 60 degrees the I1 is located. Okay, the magnitude is not relevant in this question. Okay, now regarding I2, that's again given by 120 angle minus 90 minus 30 with the impedance with an angle minus 23. So it means that this is near around minus 6 degrees also. Okay, so that's also shown as I2. Okay, now the combination is in between because the magnitudes are the same, and so and that's also shown, and then this projected backward. So now this angle that we are having here is a little beyond plus 120 degrees. So of all the answers, C is the most appropriate, which shows that 2.38 angle 143.63 should be the correct answer, because the other angles are very much distant from this particular approximate solution that we have made. Okay, so this is how we can proceed when such problems are there. So moving on to the last problem, that is 13. Here we are having one angle 0 flowing through the resistor R0. Okay, the impedance okay, I'm reading as also looking at the circuit together with you, and then ZC is minus J and ZL is 2J, which means that the overall impedance, series impedance, is going to be R, which is 1 plus J1, so predominantly inductive. So the current is going to be lagging. Okay, so and the impedance is 1 plus J. Okay, and if you are to find out the Thevenin's equivalent as is asked, the impedance is 1 plus J without doubt, and so of the 4 answers, C and D may be right. Okay, and regarding the Thevenin's voltage, this current flows through this 1 plus J. So 1 plus J is root 2 and with an angle 45 degrees. So 1 angle 0 creates a voltage root 2 angle 45 degrees. So we have D as the correct answer. Okay. So we have repeated many instances. So I'll stop for now and move on to the last of the sessions soon enough. Thank you.